Okay, hello again, Ling 341. After having conquered the world of trills and learned that basically voicing is a form of glottal trilling, we're going to move on and talk about the basics of acoustics today. Primarily because learning more about acoustics is going to help us, well, not only understand what goes on when we produce sounds, but help us transcribe those sounds a lot more easily as well. Because we don't have to simply rely on what we hear when we transcribe words, but instead we can also look and see what acoustic record of speech can show us. So that's pretty exciting, and therefore I want to get into this. But before I do have a few leftovers regarding trills. And so one thing I can mention is that when I normally ask people if there are other places of articulation for trills, when trying to lead into like the idea of glottal trills for voicing, there's usually somebody who pipes up and says, well, are there velar trills? And the answer to that is sort of. I've got an example here from an old transcription exercise of one form. Hopefully I've got the sound up for this. It sounds like this.
Gunk.
Make that a little bit louder.
Gunk.
And I think you can hear at the tail end of that, there's a K at the end of that particular word. It sounds like gunk, but you might hear that there's basically multiple release bursts there.
Gunk. Gunk.
It kind of sounds like he's releasing the K multiple times. And that's something that happens pretty commonly with velar stops. They can have multiple release bursts rather than just the ones we've seen for like other places of articulation, because that articulator, the back of the tongue, is relatively massive, especially compared to like the tip of the tongue or the lips, which you can kind of push apart pretty easily. With the back of the tongue, it's a more massive articulator. You kind of have to use both the jaw and other muscles to pull jaw and some non-jaw related muscles to pull the tongue down from the velar place of articulation, and it moves relatively slowly. So as it's moving down, you can kind of get caught up in that stream of air that's flowing through the new opening, and the Bernoulli effect can take over and pull it back there briefly as you're trying to pull it down. So you can't really produce a velar trill in a consistent way or in an intentional way. It is something that you can get, though, unintentionally, just as you're releasing a velar stop to begin with. So I've got some other examples of this. This is something we all do. It's not part of other languages or whatever. It's just part of the physics that gets involved with producing a velar stop. So I've got some examples here of former students' name production exercises. They both have nice Slavic last names that end in K. So I've got one here.
Michael Burak.
And another student.
Monica Cieslak.
And that might be hard to hear. I'll play them both again.
Michael Burak.
That K at the end.
Monica Cieslak.
They both, or those Ks at the end, both have multiple release bursts. So if I go to Michael Burak, it's a little bit of a noisy recording.
Michael Burak.
But he's got multiple release bursts for both of his
Michael
Ks.
Burak.
And you can see this here, and we're going to lead in today to start understanding what we're actually seeing in these acoustic records of speech. But here is the K in the middle of his first name. And this is the spectrogram view. This is the waveform view. And you can see these little spikes in the spectrogram. Each one of those is a release burst. And so he's kind of got a velar trill, multiple velar releases there. You might be able to hear it a little bit better for this one. Changes the place of articulation a little bit, so it sounds maybe a little bit different versus that. But either way, that's what's going on there. And in this example, we see it at the very end.
Monica Cieslak.
She kind of makes it a little bit of an aspirated or fricativized K here. So it doesn't come through the same way, but here she has two release bursts for that Cieslak K. Yeah, so this happens just kind of passively, and it can happen anytime you produce one of these segments. I've also got a little note here. So watch out for that when you're looking for velar stops in the world of acoustic phonetics. It's kind of a distinctive signature characteristic for those guys. I've also got a note here about, I talked about trying to maintain voicing, the problems we can get with that when you're trying to produce a voiced stop of some sort. Basically, it's hard to say like a voiced D or what have you for a long period of time. As you voice through the vocal folds, that voicing process is simply going to stop because of the physics involved in having sound flow from an area of high pressure to an area of low pressure, it's eventually going to balance out if it has nowhere to go on the other side of that. So another strategy to maintain voicing as opposed to, say, making implosives is to pre-nasalize the stop. And I think I mentioned that in the last lecture. And I got an example. I think it's number 4 here.
Dam.
Yeah.
Dam. Dam.
These are from the Bengali place of articulation transcription exercises. So here's the first utterance of that word.
Dam. Dam.
And this is the voiced part of the stop at the beginning. And you can hear that nice little kind of hum in her throat, as it were. The second one,
Dam. Dam. Dam.
becomes a little bit more like a
Dam.
nasal. So like I said, that's another way you can keep that voicing going. We'll listen to just this part. Might sound a little bit like an as opposed to an at your vocal folds. Yeah, we'll try it to contrast it with this guy. Yeah. So if you nasalize this stop, like here, as opposed to this, you can keep that voicing going on forever. This is a really subtle effect in this particular set of examples, but it's a common thing to find cross-linguistically that you get nasals at the same place of articulation right before voiced stops. It's simply a way to make that voicing easier. And I mentioned this before as well, but we'll go back to it again. But implosives often begin life as voice stops, and then just trying to make that voicing happen kind of forces implosion out of it, because you can make the voicing in an implosive a little bit longer than the voicing in a regular voiced stop. So yeah, trying to voice those stops completely can lead to them becoming implosives, and that's a change that happens over time in a language. So implosives are more frequently found at fronter places of articulation, and basically this is kind of one maybe legitimate reason why this is occurring, because we talked about how it's harder to voice these stops at backer places of articulation. Languages just kind of avoid having like voiced feeler stops to begin with. It's more common to find voice stops at the fronter places of articulation, like bilabials and alveolars, and those are the ones that maybe become implosives over time. So the lack of these more posterior implosives, the backer implosives, may be due to the lack of backer voiced stops to begin with. Yeah, that's a big maybe, but that's one way to kind of explain this pattern, which looks different from the kind of pattern we get for ejectives, where we find them more frequently at the backer places of articulation than in the front, like bilabials. Okay, that's all I'm going to say about that. Like I said, what I want to focus on today more is the basics of acoustics. So like I said, we can get a sense of how to read these acoustic representations of sound that we can create using a program like Prot. Okay, so we're going to start off with this basic bilabial trill scenario that I talked about in the previous lecture. So if you remember, we're bringing our lips together, and then we're increasing the air pressure inside of our mouths due to squeezing our lungs, and that will eventually force air to pop open this lip closure, like that, or like that. And as it does that, once the air flows through, it'll bring the lips back together again due to the Bernoulli effect, and we'll get this cyclical pattern where air just kind of pops out in short, sharp bursts, cyclically over time. And what we see in the outside world are these kind of wave fronts, these successive wave fronts of air pressure peaks going out to whatever surrounds our mouths as we're making this bilabial trill. So it sounds like this, in case you needed to hear that again today. But what is it going to look like sort of as that sound floats through the air? So air you can conceive of as consisting of floating air molecules, probably because that's actually what air is. I mean, it feels like empty space, but there's little molecules floating around. They're just widely spaced apart from each other. Generally speaking, the molecules are going to be evenly spaced apart from each other in the space around our lives or bodies or what have you. And they will move around a little bit, right? So they're not like perfectly evenly spaced apart from each other. And in reality, of course, this is happening in 3 dimensions, but I've got a little diagram here where I've written or drawn this out in like 1 dimension, because again, My artistic skills are quite limited, but it's good enough to get the point across. So let's conceive of these little circles as like the air molecules, which are basically evenly spaced apart from each other with a little bit of variation here and there, just due to kind of background noise, as it were. And what we want to do is push on one of these molecules. Let's say we push on the one on the left in that particular direction, going this way. What do you guys think will happen? Give me a second. It's a cold day. Anyways, yeah, you can kind of think about this like, to a certain extent, like pushing on a billiard ball. The physics still works in the same way if we have like a line of balls lined up in this fashion. But it might do a couple of things that will surprise you. So hopefully it's intuitive enough that if you push on that first molecule, that it's going to move in that direction. And then eventually it'll hit against its neighbor if its neighbor is lined up perfectly on that side of it, right? And then what happens, which is kind of interesting, is that that force that we pushed the initial molecule with will get transferred to the next molecule, and then assuming there's not a whole lot of loss of energy, that'll just keep pushing. It'll move in that direction to the next neighbor, and then eventually that one will get pushed in the direction of its next neighbor, so on and so forth. That, I think, is relatively easy to kind of understand. It's like pushing over some dominoes, or like I said, a row of billiard balls. That force will just get transferred down the line, right? The thing that's maybe a little counterintuitive, though, is that first molecule that we pushed after hitting its neighbor is actually going to come back and move past its initial rest position. So having been knocked out of this spot to begin with, it bounces further backwards than it began, basically. So that leaves us at a certain point where the second one bounces against the third molecule. The first one will be back further apart from it than where it began. So there's a big gap here in between those two molecules, even though originally there was just like an even amount of space for those two, like we see in all the rest of the molecules in the row. And to give you a sense of how this works at a macro level, like I said, we're dealing with the same physics, whether it's molecular or in human scale. And this is actually something that's kind of above human scale, because I'm going to show you this video, this old film from one of these atomic bomb videos they made back like in the 50s when they were still blowing these things up in the outside world. And so this is probably taken from like Nevada or Siberia or something like that. And they just film what happens to like these structures as an atomic bomb wavefront moves past it. So an atomic bomb obviously explodes with great intensity, but it basically is doing kind of the same thing as like air popping out of our lips when we make a bilabial trill. It's just sending a kind of intense shock wave of pressure out into the world, and then it's running, bumping up against objects that are out there. And in this case, it's going to bump up against a row of trees. And there it goes. And boom. So all these trees get pushed back in that direction. And then you notice that once the wavefront goes by, they recoil past where they were initially standing, or their vertical position, basically. And then at the end of the day, the entire world ends and nobody's happy. But we learned something in the process, right? So let's look at that little bit again. So yeah, they're standing up straight, and then the wavefront goes, and then rather than just going back to the straight up and down position, they recoil back further the other way. And they might waver a little bit as it goes by, right? Either way, don't use atomic bombs, kids. It's not healthy. All right. What does that mean for us in sound? Like I said, our initial force, our initial push is going to get transferred on down the line of air molecules, or, the three-dimensional space of molecules. And then the individual molecules would kind of waver back and forth around their initial position. So they'll get pushed in this direction until they hit something, and then they kind of go back the other way past where they started. After that second molecule gets pushed in this direction and then transfers its force down to the third one, it's going to come back to the other side of its initial rest position, and lo and behold, that first molecule will have swung back in that direction as well. So they'll meet up again. And now we have a lot of space between molecules 2 and 3, and very little space between molecules 1 and 2, and also very little space between molecules 3 and 4, right? So we're getting this kind of pattern of molecules meeting up, then a big gap, and then molecules meeting up. And eventually, if it keeps going, we'll get that same pattern repeating all the way down the line to wherever the heck it might end. So one way to think about this is this is like a bucket brigade. So in case you don't know what a bucket brigade is, I'll walk you through it. So let's say I have a fire in the form of a mini Washington Nationals helmet over here, and then I have a source of water over here on my right, and in between the water and the fire, like I want to put out the fire, right? But it's a little bit tricky. Let's say this is bigger than like a foot. It's a bit tricky if I want to, take a huge amount of water, enough that I need to like put out the fire over here. I don't want to grab it all by myself and then walk all the way back down this line. If I'm just one person, let's say I have 5 people in between the fire and the water. What I can do is set up 5 people in a row, like the air molecules, and I can have one person just get a bucket of water out of the tap or what have you, and then hand that to the person next to them, who takes it and hands it to the person next to them, so on and so forth, until they get to somebody who's at the end of the row right next to the fire, and they just like dump the water on the fire, right? And hopefully put it out. So what happens there is that the water transfers all the way from its source to the fire, and hopefully you can see these things. But the people in the bucket brigade just stay in one spot. Basically, they just kind of waver a little bit from side to side as they're taking water and handing it to the next person next to them. So they just keep doing this, but the water goes through them, right? From source to target. That is what happens in sound, right? So the air molecules that transmit the sound are kind of just staying in one spot, but the sound energy goes through them. And then we somehow perceive the pattern of sound through all that, which is pretty cool. There's a lot of things that work this way, and generally speaking, they're called waves. So a wave of force will travel down the line of molecules, and the individual molecules are going to be vibrating back and forth around an equilibrium point, basically where they began. And like I said, if this keeps going over time, we're going to get this pattern where the molecules will kind of meet up as they're at the extremes of their edges, and then extremes of their little spaces in the world. And then when they're at those extremes, they're meeting up with something, and they're far away from another neighbor too. This transfer of force is going to set up what is called a compression wave, which means that we're compressing the space between the molecules, basically. That's the point I already just made. I just got ahead of myself on the slide there. So when this happens, we have alternating areas of high pressure, which are called compressions, and we have areas of low pressure in between them, which are called rarefaction or rarefactions. So what I mean by high pressure is just that you have a lot of air molecules in a small amount of space. And what I mean by low pressure is that you have very few air molecules within a certain amount of space as well. I have an earthquake story, but I think I'll save it. Okay, so anyways, compression waves consist of alternating areas of high and low pressure in the air molecules around us. Okay, how do we know what's going on here? So we can measure the amount of pressure we have, the amount of air pressure in a particular spot, by using what you can conceive of as a pressure level meter, but what you might more colloquially know as a microphone. So microphones have diaphragms in them at a very small level, which are basically little filaments of electroconductive material, which are so thin that they will be able to kind of move back and forth in response to air pressure variations that might meet up with them. So as those air pressure variations kind of push that diaphragm or filament around, that will change the amount of electricity flowing through that diaphragm. And if you link that diaphragm up to an electrical circuit, you can record how much it's moving around by looking at the changes in electrical voltage, which go through the electrical circuit itself. So you can record those in, say, like a computer. So the diaphragm or the microphone in your computer is set up in this fashion, wherever that microphone happens to be. They all basically work in a similar way. And when you record it in a computer, you can take a look at the recording of the pressure variations you got in a program like Prot or what have you, or you could simply just play it again using an amplifier, and then you can hear what you just recorded. And it works the same way, whether it's a microphone for like the stage or like an old-fashioned tape recorder or what have you, or on your phone, so on and so forth. For ourselves, as human beings, we kind of have built-in pressure level meters, and they're called ears. And instead of having this sort of electrical circuit set up with these minuscule diaphragms or whatnot, we have eardrums, which are also basically thin fibrous material at the back end of your ear canal. As you know, it's about an inch inside your head. Don't try to touch it. You're not going to get there. And if you did, it wouldn't be good news anyways. But the eardrums are capable of moving back and forth in response to air pressure variations that go inside of our heads, right? They are connected up to a series of tiny little bones called the ossicles, which are actually the smallest bones in your entire body. And those bones will respond to those vibrations by vibrating back and forth themselves. And the bones, in turn, are connected to a structure called the cochlea deep inside your head, which has fluid in it. And then that fluid gets pushed around by the motions of the ossicles, and those fluid motions get converted into neurochemical signals in your brain. And eventually you perceive all of this as sound. So it's not going to work exactly like it will for a microphone, because you can't, say, hook this up to an electrical circuit in the same way you can a microphone. You can't simply record what your ears are perceiving in the same way as you can in a computer. But you get the same sort of sensation out of that. When your ears respond to air pressure variations in the world, we experience those as sound. And it's nice that we have this technology to sort of record those air pressure variations with microphones, but it doesn't work in the exact same way as it works for your ears. It works in a very similar way. Okay, so that's sound. And let's say we have this kind of setup where we have air molecules vibrating back and forth. And then we kind of get these alternating patterns of high pressure or compressions, followed by rarefactions, and then another compression, followed by a rarefaction, so on and so forth. I'm moving in time this way. So this is earliest to latest. And let's say we have our pressure level meter here at just one spot, and it's experiencing or recording these sorts of fluctuations in air pressure as it goes through time. What do you think the output of that would look like? Say if this is my microphone or maybe my ear, and I found a way to record my ear's perceptions of things. What would the output of this pressure level meter look like? I'll give you a second to think about it. And maybe you have intuited the answer. I hope you did. But either way, this is the way that air pressure would change over time. And this is a sort of specific shape of wave that you may have encountered in math class in high school or what have you, that's called a sine wave, sorry. So the reading on the pressure level meter is going to fluctuate between high and low pressure values. And in the simplest case, the variations will look like a sine wave, which sounds like this. It's a very kind of simple sound. Sometimes they call it a pure tone. And it's not super exciting for sure. I will make a point here in case of any of you math geeks out there are getting really upset at me for calling this a sine wave. Actually, a sine wave should start at 0 and then go up, but follow the same basic pattern. The reason I have this one starting at 1 is because of the way I drew up this diagram. So it starts with high pressure here and then goes down to low and then back and forth like that. The thing about this is that it has these sort of smooth variations between high and low pressure. It's nice and kind of curvilinear. And it actually winds up being sort of the most basic form of sound we can work with in acoustic phonetics, which is why I'm starting with that. But I do want you to think for a second about this representation. So what I'm showing here are changes in air pressure, or recordings of those changes in a computer. And this is change in time on the x-axis. So in the y-axis, we have changes in air pressure. High means higher pressure, low means lower pressure, and this is just how the whole wave progresses over time. Okay, so this is called a waveform. We'll come back to it. I think I've talked about it before, but we're going to look at a lot of those in class, so make sure you understand what's actually being shown there. All right, so sine waves are periodic, which means that they recur over time. So yeah, you see the same pattern happening over and over again in a sine wave. That's all I mean by by periodic. If they were aperiodic, we'd see different patterns in different points in time, basically. But since sine waves are periodic, that means that they have a period, which is the amount of time it takes for the pattern to repeat itself. We talked about these the other day. I want to talk about them again because the period has a clear relationship with the frequency, which is another property of a sine wave. So the frequency is just the number of times within a given time frame that the pattern repeats itself. So I'm talking about this with respect to sine waves, but other kinds of waves can be periodic, and they also have both of these properties associated with them, the period and their frequency. So frequency will equal 1 over the period, just like period equals 1 over the frequency. Normally, you would measure frequency, especially for our purposes, in cycles per second or hertz. So how many times in a second does this pattern repeat itself? The way I've defined frequency here, I talk about within a given time frame. And I think I mentioned this the other day, but you could also say, like, what is the frequency, the number of times we meet in class during a week? And the frequency could be 3 times a week, something like that. A week is far too big of a time frame for us to be thinking about for the frequencies we need to deal with in this class. For our purposes, we will think about them in terms of a second time frame. How many times do they repeat within that time frame? And I think I gave you some examples, like for the average sort of frequency for vocal fold vibrations when different kinds of speakers are speaking. So like for an adult male, it's typical to get a fundamental frequency of 120 hertz, which means a relatively low pitch, basically. But that's saying that a male speaker's vocal folds will open and close 120 times a second. Or an adult female speaker's vocal folds will open and close 220 times per second. It's a lot of times per second, so these things go by pretty quickly. And the other property I want to mention here is amplitude or peak amplitude. So the peak amplitude is the maximum amount of vertical displacement in the wave, which is either the maximum or minimum amount of pressure. And I can go back to this. So I've labeled this y-axis here as pressure, but in a more general mathematical sense, you can think of this as amplitude. Basically, how much change are we getting in that y dimension? And the peak amplitude is just going from 0 to this peak here. How much change in pressure do you get there? How much change in amplitude do you get from sort of the baseline to the top? And it's going to be the exact same amount, whether you go from 0 to the top or go from 0 to the bottom, which is why I said that this could be either the maximum or the minimum. And if you wanted to talk about going from maximum to minimum, you could. That's called peak to peak amplitude instead. So amplitude is just generally like, where are you on the y-axis? Where are you in the y dimension? But peak amplitude is what value to get at the very top and bottom of this waveform. Okay, a waveform, just I'm defining it here, but we're going to plot amplitude on the y-axis against time on the x-axis. And this is just another example of what this looks like with a real sine wave that starts at 0 here. And this shows you as well that this is our peak amplitude going from 0 to the top. And then I've got one cycle going from 0 here to, well, time 0.01 here, but it starts at the exact same spot, right? This whole cycle concludes here because it's going to begin again at this point. And my period here, going from 0 to 0.01 seconds, is 1/100th of a second. It's 0.01 seconds. That's how long it takes me to complete this cycle. So it's 1 over 100, and this already gives you the answer for what the frequency is. So if I can complete a period in 1/100th of a second, that means I can complete 100 cycles in a second. So the frequency of this guy is 100 hertz. Hopefully that makes sense, but if it didn't, rewind and watch it again, and hopefully it'll fall into place. Okay, so I've got an example here of the next step up. What we can do with sine waves, we can make them into complex waves by adding them together. So when more than one sine wave gets combined, they're going to form a complex wave. And the math for this is actually really quite simple. All it involves is addition. What may get confusing, if at all, is just sort of the notation that I use to kind of describe that process. But let's say I have sine wave 1. I have two sine waves, 1 and 2. And I look at that sine wave and I determine its amplitude value at some particular point in time, like time 1. So let's say, I'm dealing with the amplitude value of this guy right at its peak, which is, I don't know, like at 0.3 seconds or something like that. I want to add it to another sine wave 2, which is not going to look the same as the one we saw on the previous slide. And what I do is I take the amplitude value of that second sine wave at the same time, like 0.3, whatever that happens to be. And so I'm going to denote that amplitude value, or these amplitude values, as, for the first one, it's a sub 1, the amplitude value at time 1 for sine wave 1. So this one refers to the time, so it stays the same for both of these guys. And this number 1 refers to which sine wave I'm dealing with. So this is amplitude value for sine wave 1. This is amplitude value for sine wave 2 at that time. And then, like I said, to get the amplitude value of the complex wave, you just add those two amplitude values together. So at time 1, the complex wave's amplitude value will be the amplitude value for the first sine wave at that time, plus the amplitude value of the second sine wave at that time as well. Okay, that's a lot of formalism, basically here to help make this mathematically clear for you in case you would ever need to add these things together. For instance, I want to show you a graphical example of what this looks like, which might be a little bit easier to understand. So let's say I have this sine wave, or this waveform in general, and we see it has this nice consistent pattern again. I'm going to call this one a high amplitude waveform because it goes all the way up to 1 at its peak and goes down to -1 at its lower peak. And then it has low frequency because within this time frame it's only repeating 4 times. So we can compare that to a second waveform, which looks like this. And this one is low amplitude because it's only going up to about a half here on the y-axis, or down to -1/2 on the bottom end. And it repeats a lot more quickly. It repeats a lot more times within this same time frame. So I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, whereas this one is repeating 4 times. So if this were a second time frame for both these guys, we'd say this one has 4 hertz frequency and this one has 12 hertz frequency. But what I want to focus on now is what happens when we add them together, and we get this sort of complex shape when that happens. So at the top, we get this sort of broader pattern that we see in our first sine wave, but then we also see this kind of smaller pattern superimposed on top of that, which is kind of neat. And then it just kind of bounces back and forth, again, in a consistent fashion. It's periodic. It's just not a sine wave anymore. It's not this nice smooth change from top to bottom over and over again. Instead, we get this kind of loop-de-loop thing in the middle. That's why it's complex rather than a sine wave. That's why it's not called a pure tone anymore. And it would actually sound a little bit different too. So I can actually show you how we can make one of these guys using Prot. So in Prot, rather than opening a sound file or listening to it, that sort of thing, you can create a sound. So I've got an option of creating a sound as a pure tone. We can play around with that. This will be a 440 hertz sine wave. We'll just hit OK. And it should sound like the sine waves I've been playing already, right? And they kind of dampen it a bit on the edge, but here it is. Yeah, let's make it a little bit longer than that. It looks like a sine wave, right? That's the idea. Let's create 2 new sine waves from scratch. Yeah, and I'll do it this way. So the way we create this from a formula is that this number here is going to be, this number in the front is going to be the peak amplitude of the sine wave, and this number here in the middle of this parenthetical expression is going to be the frequency. So this corresponds to that big sine wave, the first sine wave I showed you on the previous slide, with an amplitude of 1, peak amplitude of 1, and a frequency of 4. Okay, and we can look at it, and it should look pretty similar to what we saw on the slide, right? It should look like that guy. You can't hear it 4 hertz is actually too slow for us to perceive it as a sound. If we're a bit louder, we might hear it as like a series of 4 beeps going by pretty quick. But we're out of luck in this particular case. So in the second example, I'm going to create a sine wave of 12 hertz. That's the frequency, and its peak amplitude is 0.5. And we can look at that. And there we go. It's not going to look smaller. You have to kind of intuit that. So you notice that here, my peak amplitude, or the prod just adjusts and plots this thing out to its peak amplitude. So there's no like empty space on the top or the bottom. So this one gets adjusted to 0.5, but it is smaller in terms of, or less intense in terms of its amplitude. And then it repeats more often during the same time frame. So both of these are plotted out for a second. Yeah, and maybe you can hear my computer kind of blah, 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 doing that sort of thing when I start it and stop it, but that's not really sound. Not really the sound that's being represented. Lastly, I'm going to combine these two together. And like I said, we do this just by addition. So we'll do it like 4 and 12 hertz. And this one is 4 hertz with peak amplitude of 1. And the rest of it stays as it was for sine wave 2. We can add those together, and we get this. Yeah, now you can hear that beeping a little bit. Right, it doesn't really sound like a sound. It sounds like something vibrating in the background, I guess. But we get that kind of funky little like dip and dipsy-do at the bottom and top of this thing. So it's not a sine wave anymore, basically. That's how you create a complex wave. I've got another example here. We'll see what you make out of this one. So here is a 480 hertz tone. Oops, this may not work. At least not that way. So I'll play you this sine wave and this sine wave. And I'll play them again. What do you think happens when we add those two together? Yeah, we get a dial tone. So that might be a bit anachronistic, but if you've ever used a touch tone phone, it basically operates on the basis of combining different kinds of sine waves together, 2 for each number or letter button that you would press on a phone. And that just means that nothing's going on there at the bottom. Yeah, so that's kind of fun. The phone system, or at least the old phone system, was not nearly as complicated as you might have thought. They're just using basic acoustic phonetics to make it work, or basic acoustics to make it work. Okay, this leads me to the concept of fundamental frequency. I think I mentioned that a minute ago when I was talking about the different fundamental frequencies we get for, say, adult male speakers versus adult female speakers, so on and so forth. The fundamental frequency of a complex wave is simply the frequency at which the complex wave repeats itself. So we know from our previous example that when we create a complex wave, it's not necessarily going to look like a sine wave anymore. It's not going to be nice and smooth. It could have funny little bumps here and there. But if it's periodic, you will see the complex pattern repeating itself over time. And the frequency with which that pattern repeats itself over time is the fundamental frequency of the complex wave. This has a mathematical property. It so turns out that the fundamental frequency of a complex wave is going to be the greatest common denominator of the frequencies of the waves you added to make that complex wave up, which I'm calling the component waves here. So in the previous case, I gave you an example of adding a 4 hertz wave to a 12 hertz wave. The 4 hertz wave and the 12 hertz wave I'm calling the component waves, the component sine waves. And then on the basis of that, we'll get a fundamental frequency for that complex wave. In case you aren't familiar with this term, greatest common denominator, or just can't remember what it might mean, I've got a definition for that as well. So greatest common denominator is the largest number that 2 or more numbers can be divided by to yield an integer that is a whole number value. So let's take the case of the complex wave we just made up, where we have a 4 hertz wave and a 12 hertz wave. What is the biggest number that you can divide those two numbers by and still come up with a whole number? I'll let you think about it for a second. That one's relatively easy though. So the biggest number in that case is 4. So you can divide 4 by 4 and get 1. That's a whole number. You can divide 12 by 4 and get 3. That's a whole number as well, right? If you know, I was adding a 5 hertz wave and a 12 hertz wave together, I couldn't divide them both by 4 and get any kind of whole number, right? So 5 divided by 4 is not 1. 12 divided by 4 is still 3, but 5. Yeah. So that wouldn't work, right? It's got to be the biggest number you can use to divide both of those numbers by and still get a whole number out of the process. And that's an easy example. So let's take a slightly more complicated one and say, what's the fundamental frequency of a complex wave that consists of 600 hertz and 800 hertz tones? Yeah. If you're comfortable with the math, this might not be too hard. I'll let you think about it as I show it to you by creating that sound from a formula here. So I'm going to do something similar here and create a complex wave out of a 600 hertz sine wave and an 800 hertz sine wave. In this case, I'm going to make the peak amplitudes the same in both cases. And we'll change the name. Yeah, so what's the biggest number you can divide both 600 and 800 by and get a whole number in both cases? Right. Hopefully you figured out that it's 200. So 600 divided by 200 is 3. 800 divided by 200 is 4. And I'll play this one for you. Yeah, that was annoying. Sorry. Should have told you to turn your volume down. Maybe that's slightly better. But when we play that, hopefully you can hear the kind of two tones in there. One slightly higher frequency than the other. And if we look at it, we should see a complex pattern repeating itself over time. And we do. That's just a very short amount of it. One of the funny things to think about, though, is like, what should the period of this guy be? So I'm saying the fundamental frequency should be that greatest common denominator. It should be 200, which means that the fundamental frequency is 200 hertz. If we can repeat the pattern 200 times in a second, how long does it take to repeat the pattern? It should only take 1/200th of a second, right? So let's zoom in real close here. This is our funky little pattern. The first one starts here at 0. The second one starts right about here. And it turns out it's right at about 0.005 seconds, which is 1/200th of a second. This pattern here. It's hard to click exactly on that point perfectly, but that's the pattern we see. The math I gave you is right. Turns out I'm not lying. And just to prove that, let's try it again with a complex wave consisting of 120 hertz and 150 hertz tones. What is the greatest common denominator of 120 and 150? I'll let you think about that as I put together the formula. And we'll listen to this as well. Hopefully it won't be as annoying the first time we go through it. Got 120 and 150. So these are going to be lower frequency tones. You should notice that they won't sound quite as high. Yeah, sorry, that was a mess. Yeah, so it's harder to hear. I can't win with the obnoxiousness today. And yeah, you might get a little bit of a sense that there's a wavering there too, so that makes it hard to hear both tones kind of separately. But hopefully you can hear two tones in there. Okay, so what is the greatest common denominator of 120 and 150? Turns out it's 30. So you divide 120 by 30, you get 4. You divide 150 by 30, you get 5, right? So 30 hertz should be our frequency for this guy. If 30 hertz is the fundamental frequency, the period should be 1/30. 1/30 is something like 0.033 in decimals. Here's our complex pattern. Here's where the second complex pattern or second repetition of it begins. And I get 0.033, so on and so forth, right? And the math is right where we expect it to be, right? So you might not like math, but it can be useful, especially when we do acoustic phonetics. I'm going to say as well, the fundamental frequency of this guy is 30 hertz. That's getting close to the limit of like the lowest frequency that we can hear. And when you go lower than about 20 hertz, you stop hearing frequency as like a tone, and you start hearing it as like the individual beats, the individual repetitions of the pattern. So that may be why you're hearing this as sort of like kind of having beats in the background rather than just two pure tones. Kind of like that. Okay, cool. That's how the math works. Greatest common denominator will give you the fundamental frequency of a complex wave. Okay, so why am I talking about this? It turns out that in speech, the fundamental frequency of voiced sounds is based on the rate at which the vocal folds open and close. So this is looking at sort of a microscopic level of what happens when your vocal folds open and close during voicing. And it turns out they don't simply like open in one nice clear pop and then close in that one nice fell swoop, as it were. There's some complexity in there. There's a bit of messiness, and this is showing you that rather than just sort of one nice clear wave front that comes out of the vocal folds, we get kind of a complex pattern, which is not necessarily going to repeat perfectly exactly the same way every single time, but it's going to be close to something like that. So we start out in voicing just by getting a complex wave. And it turns out one of the nice features of that is that you can kind of break it down into sine waves, but that's getting a bit ahead of ourselves, but that will be a very convenient feature of analyzing speech as we go. So I've got a visualization of what this looks like, comparing what voicing looks like in terms of its complexity with a combination of a 100 hertz and a 300 hertz wave. So this is going back to basically the pattern we saw before with the big loopy low frequency pattern and then kind of these higher frequency smaller pattern superimposed on top of it. So that's complex. It's not a sine wave, right? But if you look at voicing, what happens when the vocal folds open and close, you get something that's a lot more complex than that, or it's a lot more angular, I guess you could say. So this is actually something that's recorded by placing electrodes around a person's neck and recording like how much the vocal folds open and close. Another sort of grotesque way to think about that, we're coming up on Halloween here when I'm recording this, but if you think about just like removing a person's head from their body and still forcing air through their vocal folds, again, don't try that at home either. Then what would happen to the vocal folds is that they would kind of open and close in this sort of pattern. It doesn't really look like a nice curvy sine wave at all, right? But you can see that periodicity. You can see the repetition over time. It's a complex pattern. And therefore we have to think about like all those sine waves that go together to make that complex pattern up. Okay, and why do you care about this? It turns out that changing that fundamental frequency in speech can have linguistic meaning. And this is something we do every day of our lives all the time. Whenever we speak, we change our fundamental frequency on the fly as we go. And this has particular importance for what are called the suprasegmental or prosodic features of speech, like things like tone or pitch accent, stress, and intonation. And this is exactly what we're going to cover next, now that we kind of have a sense of like where it's coming from and what it looks like, at least in an acoustic representation. So you can modulate or change fundamental frequency relatively independently of what's going on with the vowels and consonants up higher in your mouth or in your vocal tract. So for that reason, these linguistic properties are often referred to as suprasegmentals. And we're going to touch upon those next, kind of focusing on how the changes in fundamental frequency correspond to like differences in linguistic meaning for languages that have tone distinctions or pitch accent distinctions, and eventually languages like English, which have stress-based distinctions. So that's what we have to look forward to, and basically the foundation of that whole analysis will be acoustic phonetics. So we'll just see more and more of these representations as we go. I hope you're looking forward to it because I'm looking forward to it a lot too. So I'll see you guys next time.